50 minut mogę mówić?
Tak. Lub mniej.
50, lub mniej. W 45 to się nie zamknie.
Z taką precyzją.
Nie ma nikogo po angielsku. Może to po polsku, bo tak?
Chyba, że mówisz coś w świat.
To jak chcecie. I can speak English. Ale trochę to zawsze dziwne mówić do Polaków. Jest po angielsku.
Może zaczniemy w takim razie. So it's a great pleasure to have today with us Professor Andrzej Wereszczyński. Andrzej will talk about self-dual impurities, BPS, and I think this is Woldomolny Prussia zone of yes? As far as I remember.
Yeah. Thank you. Thank you very much for the invitation. For me, self-duality is exactly the same as BPS. So I will change this. Yeah, I will use both names. And this topic is really very fresh topic. We discovered these things quite recently, and some features, some results are from the last week. So it's like a positive Pandora box. Whatever we touch, the nice mathematical structures or results pop out, and yeah, we are really happy. Oops. And so this talk is based on the collaboration with Kasia Oleś, with Tomek Romanciukiewicz, they are from our institute, and Christoph Adam from Santiago de Compostela, and Jose Queiruga from Karlsruhe Technology Institute of Technology or something. Okay, so very quickly about the outline of my talk. I will define what self-duality means, and then I will consider a general impurity which usually breaks self-duality completely, and then I will show how to add quite general impurity, but in such a way that half of the self-duality is present. And it's really quite spectacular. It's fantastic, because it's quite simply, it's almost as simple as in the case of a usual self-dual model, but it adds new, very non-trivial features. Okay? So it's very nice. And then I will show some applications of this self-duality, self-dual coupling of impurity. But in principle, this way of coupling of an impurity is arbitrary. It can be applied to any original BPS or self-dual theory. Okay? So what self-duality means? And I will concentrate myself only to 1 + 1 dimensional models because of simplicity, but it can be considered also in higher dimensions. Okay. Just standard scalar field theory, so one scalar field in 1 dimension. I ignore time dependence for a while. You can add it. You can consider relativistic field theory, you can consider non-relativistic, it doesn't matter for many of the results. Okay, so the energy consists of 2 terms. This is a gradient term, we call it kinetic term, and potential. And I will need a potential which has 2 vacua. Okay? So I need at least 2 vacua. So I need a potential which has 2 points isolated where my field takes the vacuum value. Okay? Basically, V, potential U. Okay. I need it because I want to consider topological solitons, which are objects which connect one vacuum with another one. Okay? they interpolate between two vacua, so they, if you consider how they look spatially, they are almost all the time, I mean, everywhere they are in the vacua, but there is a small region where the field goes from one vacuum to the other vacuum. And then in this little blob, the soliton is localized, usually exponentially or power-like localized, and almost all energy density is kept in this region. So solitons are, they are like field theoretical description of particles, in a sense, right? And I can associate a topological charge, which is a charge not like a netter charge related to any continuous symmetry, but it's related to the topology of the space, time, and target space I have in the system. Okay? So in 1 + 1 dimensions, and with these two, or with a potential which has discrete number, even infinite number of vacua, topological charge is just a difference between the asymptotical values of the field. Okay? If field in my, if I have a solution which goes from one vacuum to the same vacuum, then the topological charge is 0. But if it goes from one to the other one, then the topological charge is not 0, and there is a current which corresponds to this charge, and this current is conserved, and in principle it means that you cannot deform one solid, you cannot kill the topological charge. So once you have a soliton, a solution with topological charge non-zero, then you cannot deform it continuously to something which has 0 topological charge. Okay? So you have different, isolated, in a sense, sectors numbered by topological numbers. Okay, and topological solitons, which are this localized object, which goes from one vacuum to the other one, we call it kinks, okay, in 1 + 1 dimensions. Okay, good. And then one very interesting thing, or observation in 1 + 1 dimensions with arbitrary potential is that the original field theory can be rewritten in this form. Okay? The static energy can be put in this, this form where you have this positive definite function, and you have to subtract the cross product between these two terms, right? Because then you have phi x squared 1/2, which is the kinetic term for the original energy, and then you have the potential, but then you have this mixed term which you have to subtract adding this integral, okay? And you are back with the original energy integral. But this term is positive definite, okay? So it's always bigger than 0. So of course this expression is bounded from the below by this expression. But here is space integral, but you can change the space integral into the target space integral. Now you integrate over the field, okay? So it doesn't matter how the field is, how the field depends in your space. What does matter is the asymptotic values of the field and the theory you have, which is the potential. Okay? So this object is just an integral which depends only on your theory and the asymptotical values of the field. And therefore it depends, I mean, I denote this target space integral as this average value. You can put it in this, yeah, you can understand this integral as a target space average value multiplied by the topological charge. Because if the asymptotical values are the same, then this integral is 0, because it's integral from the same point on the target space to the same point on the target space. It's 0. But such objects have 0 topological charge. Good. So the energy is always bounded from the below by the topological charge, and number which is computed for your theory. Right? It's just a number in your theory. Once you assume the potential, it's just a number. Okay, but then this lower energy bound can be attained for the solutions of this equation. Because if this integral vanishes, okay, then it's not the lower bound, it's just equality. Okay, this equation is first order equation. It's not like usual Lagrange-Euler equations, which are second order, okay? But it's first order equation. Of course, solutions of this, maybe not of course, but solutions of this equation are also solutions of the full Euler-Lagrange equations. You can act with derivative, and then use again the Bogomolny equation, and then you can show that finally you get the full Euler-Lagrange equation. So all solutions of this equation are necessary solutions of the full dynamics. Okay? Good. Okay, and this equation I call Bogomolny equation. And it has very nice feature that it's lower order equation. So it's always easier to solve first order equation than second order equation. That's one advantage. Another one is that your energy bound is saturated, which means that if you have a solution with a given topological charge, this is a stable solution. You cannot find something which is lighter than this solution, right? Because in a given topological sector, the bound is attained. You cannot find something with smaller energy. So this solution is topological, it's stable because of topological arguments. Okay? That's fantastic. So my BPS or self-dual solution is a solution of a lower order Bogomolny equation which saturates a topological bound. In fact, this equation implies a sort of non-interacting limit which in one dimension is equivalent to zero pressure condition, but this is not, it's just observation, and energy is fixed by the asymptotic behavior of the field, okay, but not, it's the local distribution of the field is immaterial. And a model is BPS if it has a sector with BPS solutions, okay? Because of course these BPS solutions are not the whole story about solutions of your theory. There can be non-BPS solutions.
What does it come from?
BPS is Bogomolny, Prasad, Sommerfeld.
Okay.
Yeah, it's this famous monopole, which is an example of BPS solution. So, of course, this BPS type models, they exist in higher dimensions as well. Right? And they are very famous because in higher dimensions they are very rare and they somehow capture very important mathematical and physical features of theories. Okay? So, like CP1 model in one dimensions, famous Abelian-Higgs model at critical coupling, which means that vortices again don't interact. Polyakov monopole, Young mixed instantons, many of examples. And there are really, all the time they are quite important because of the simplicity and because the fact that they capture many interesting and important features. So, but in 1+1 dimensions, everything is BPS. Any theory has BPS sector. This is, in a sense, weird. It's not nice because it's completely parallel to higher dimensions. In higher dimensions, it's very exceptional. In 1+1 dimensions, any theory you can write down has BPS sector. Oh, that's boring. If everyone has something, then no one wants to have it. Right? So you can deform potential. Any potential can be considered. You can consider any target space, any number of fields, and they can form any kind of very complicated target space manifold. You can even deform your energy functional and have any function of space derivatives. You can also put higher space derivatives. Well, these models are not maybe very interesting, but yeah, you can deform models in such a way. So it's really not so nice.
So what spoils this for higher dimensions?
One difference, I don't know what spoils, but one difference is that in 1 + 1 dimensions, the BPS sector is always one soliton sector, and this is important for me. It's only one soliton. You never have, there are no examples with, for instance, static 2 soliton configuration. Right? In higher dimensions, you have, for instance, if you take vortices or instantons, you can have solutions with arbitrary topological charge.
Okay.
So that's the main difference. But I don't have really like mathematical deep reason for that. Okay? This is related. So BPSness or self-duality in 1 + 1 dimension is really a generic feature. It's nothing.
Why is it called self-duality? Okay.
Because it relates something with something else, and these both terms combines to topological charge, okay, or density, and then you can relate. Yeah.
By duality means also anti-self.
It's like it comes from instantons when you have like F-mu tensor and dual tensor, and then instantons are solutions of the self-dual that the tensor equals to the dual tensor. But here, a dual a dual object to derivative, the field derivative is exactly potential. So it's also self-duality. Okay, but in 1 + 1 dimension, as I said, only charge 1 or -1 soliton is in the BPS sector. It's just pure lonely soliton lives in BPS sector. Okay? It's soliton, which goes from -1 to 1, for instance. Of course, your model is Lorentz invariant, for instance, or energy density is a translational invariant, so you can always put your soliton in arbitrary position. Okay? Which means that you have a moduli space, which is a space of fields such that they have exactly the same energy. Right? But this moduli space is trivial because it consists of solitons which are put in different positions, but they have exactly the same shape, they vibrate exactly the same, they are really the same objects. So no structure in this moduli space. Okay? This is now we think that this fact, this trivial moduli space, is really this non-triviality of the moduli space we found for our impurity is really the fantastic, the crucial observation. But once again, in 1 + 1 dimensions, the moduli space of energetically equivalent solutions is trivial, is boring. Okay. So how to destroy the BPS, the self-duality in 1 + 1 dimensions? You have to break the translational invariance. You have to add an impurity. And there are infinitely many ways to couple an impurity. Okay? One way is that you multiply your field by impurity, and then it enters into the Euler-Lagrange equation in such a way. Okay? So an impurity is a given space distribution of something. Okay? It can be a barrier, it can be a well, it can be something more complicated.
But usually impurity means something very small. And here,
Here, it can be anything. It can be
arbitrary.
arbitrary. Okay? It can be delta. It can be Dirac delta. It can be whatever, right? But once you add your impurity, the translational invariance is broken, okay? And there are no BPS solutions. If, for instance, if you consider this kink and then add an impurity, then such a kink will be attracted or repelled from the impurity. And and for instance, the moduli space is empty because there's only one position in space which is dynamically decided. Okay? So no BPS structure, no moduli space, and that's alive. And that's the picture we had for self-dual models before. That we have self-dual models without impurity and everything is BPS and with trivial moduli space. And if you add impurity, then translational invariance is broken, nothing is BPS, and no moduli space. Here is boring because everyone has it. Here is boring because no one has it. Okay, and now a story about self-duality preserving defects or impurities. Strictly speaking, it's half of the self-duality, which is also very nice. Right? Sorry?
What do you mean half?
I will explain everything. I'm really excited. Okay. So we want to restore the self-duality. So for that, we have to add two terms to your Lagrangian, or energy. One is, and both mean coupling to your impurity. One is a sort of usual coupling of impurity. Here is impurity multiplied by a function of field. That's usual coupling of an impurity, and this coupling is considered in experimental setups, in theoretical, so that's usual. Another one is to add this term, right? But this term is not so weird term, because if sigma is a constant, it's just a total derivative or derivative of the field, and then it doesn't contribute to your equations of motion, because it's total derivative, okay? Or it contributes like topological expression, okay? But for us, sigma, which is impurity, is space dependent. And then this term is not any longer a total derivative, it cannot be integrated out, and it will contribute to equations of motion, okay? And there is a third term, which depends only on your impurity, so it doesn't contribute to equation of motion. It just sets the zero level of the energy, for instance. So we need those two terms, but they are not really weird terms. And we have at least one experimental setup in which it can be realized. And we are working on another applications. Okay?
So basically you can eliminate impurity, yes, from this. Because
now you have this term which multiplies, this is a function of the
but
potential.
from the equations of motion, so you could later, because there is no spatial derivative.
No. Sigma depends on x, on...
Okay.
So then it's another field, just another
It's just another field, yes.
It's just another field, but without any dynamics.
Okay.
It's fixed, okay? It's
a
not...
mean field, background field.
It could be background field, it can be external field, it can be something, okay?
Okay. No dynamics, yes.
Good. But the point is that the spatial distribution of this impurity is not restricted. So this is important from experimental point of view, because it gives a chance that such a theory can be really found in some condensed matter system, for instance. And the potential, the original potential is also unrestricted. So we have this kind of theory. And now, the nice fact is that, again, it can be combined in something which is positive definite and something which is the topological. Okay? Now, W is another function of the field. And once again, this is a positive term, so we have, it can be bounded from the below by this expression. And this can be written as a topological charge, and again, target space integral. But remember, before, when we had Bogomolna equation, we had two ways of doing this trick. You could have plus and minus sign, and minus and plus, which gave you plus and minus sign for the Bogomolna equation, and there are two Bogomolna equations, right? One corresponds to king, which goes from this to that, and another one is anti-king, which goes backward, okay? So, but now you have only one Bogomolna equation. There's only one equation which saturates this bound. So only king or anti-king can be a BPS solution. So, huge asymmetry. Okay? And again, you can show that, of course, the Bogomolna equation implies the full equation of motion. Okay? So, quite similar, but not completely. Only one Bogomolna equation. So, yeah, we have both BPS and non-BPS solitons in our theory. If this additional function W is just square root of the potential, then this is square root of the potential, then I always assume that sigma is exponentially localized. So asymptotically, it doesn't matter. It doesn't contribute. So then, this is a square root of the potential, so it's always positive. Positive plus something must be 0, which means that the derivative must be always negative, right? Which means that your solution must have a negative derivative. So it must be like that, from plus 1 to minus 1, okay? Which is anti-king. It goes from it has minus topological charge, from bigger vacuum to smaller vacuum. Okay? So in this case, the king, I mean the anti-king, okay, is a BPS soliton, while the king is non-BPS. It doesn't saturate any topological bound. It doesn't obey first order equation. It does obey second order equation, of course. Okay. So this non-BPS soliton behaves as usually soliton behaves in the when you add impurity. But this BPS soliton doesn't interact with your impurity at all. Okay? It can be. It has again this nice feature that it can be put in any distance from your impurity, and then all these configurations have exactly the same energy. Okay? And there is also lamps which are topologically trivial solutions. They correspond to this vacuum solutions from the original non-impurity theory, but now the vacuum field, for instance from -1, must be somehow deformed in the vicinity of your impurity, right? And then goes back to the vacuum. Okay. Good. Okay. So this BPS king, as I said, can be put in any position from your impurity. So you have something which is a sort of generalized translational invariance, which is not as simple as in the usual Lorentz invariant setup, right, theory. But because I will show you some picture, but once king is approaching the impurity, it's deformed, of course. It changes its shape, okay? And go, yeah. But the energy is exactly the same. All the time you have the same, the same energy, from the energetical point of view, you have the same configurations.
What mechanism gives you the scale of x0?
This is an arbitrary position of the king with respect to the impurity, and it's arbitrary. It's arbitrary. So there is no static force between soliton, the BPS soliton, and the impurity. Which means that you have the moduli space. Although you added an impurity, you have moduli space. And and the biggest discovery now we think is that this moduli space is non-trivial. Although energy is all the time constant, the way how the king vibrates changes. And this is really like diamond if you want to analyze interaction between solitons and solitons. Not really with impurities, but with solitons. In an almost analytical and well-defined way. Okay. Examples.
And does it exist only in 1 plus 1 dimension?
No. You can do it in higher dimensions as well. Examples. First example is sine-Gordon model. This is a model which has infinitely many vacua. Okay? They are degenerate. So it's 0, 2 pi, 4 pi, and the potential is 1 minus cosine phi. This is a famous model because it's an example of an integrable model. And for this sine-Gordon, sine-Gordon, the usual sine-Gordon is just these two terms, where the W, the prepotential, is sine squared.
This is potential, yeah?
This is a potential, yeah, because sine squared is 1 minus cosine. Here is phi over 2. Okay? And now we add these two terms to have an impurity model, which is half BPS. Okay? Okay, so W is now sine phi over 2. This term, usually in the sine-Gordon model, you have king from 0 to 2 pi and anti-king from 2 pi to 0 and nothing more, right? Because the model has this symmetry 2 pi translation in the target space. But here, adding this prepotential and this coupling, especially, it breaks this 2 pi symmetry. Now the model has 4 pi symmetry. It's just peculiarity of this model. It doesn't matter for general features of the self-dual impurity models. But you have to remember that now you have, instead of 2 types solitons in the original model, which both are BPS, you have 4 solitons, and again 2 are BPS and 2 are not BPS. Right? So